What's up, students? Today I want to look at a combination circuit, and we're pretty much going to figure out and answer all the questions we could possibly answer when it comes to this combination circuit. We're going to be able to determine the current, which is I, through each resistor, the voltage drop V across each resistor, and also the power dissipated P across each resistor. And guys, just remember, dissipated, that just means given off. Fancy word. Now, what I'm going to do first, and this is what I'm going to do for every single combination circuit, is I'm going to try and break down more complex things like this parallel circuit, and I'm going to try and make this circuit as simple as possible and then work backwards. And each time I do so, I'm going to redraw this. So the first thing I'm going to do is I'm going to make this parallel circuit into one resistor. So I'm going to find the equivalent resistor of R2 and R3. So to do so, I'm going to say that REQ, 1 over REQ, is equal to 1 over R2 plus 1 over R3. So that's going to equal 1 over 3 plus 1 over 6. So that's going to be 2 over 6 plus 1 over 6, which is 3 over 6. Now remember, guys, this is 1 over, so REQ is actually 6 over 3 ohms. So now I can rewrite this circuit as a series circuit and not a parallel circuit. And on this circuit, the voltage will remain the same, but now I can write this as R1 equals 4 ohms and R2 as 2 ohms. Now, although this is a series circuit, it's still pretty easy to work with, but I'm going to make it even easier, and I'm going to combine R1, R2 into an equivalent resistance as well. And in series, that's super easy. We just take the sum. So I'm not going to work out the math. I'm just going to redraw this as one resistor with the same exact voltage, V equals 12 volts. But now the equivalent resistance is going to be equal to 6 ohms. So that's essentially going to be the total voltage and the total resistance of this circuit. But we want to know the current through each. We know the resistance already. So what I'm going to do is I'm going to use V equals IR, and I'm going to solve for the current through this resistor, which essentially is going to be the total current. I is going to be equal to 12 over 6, which is going to be 2 amps. Once I have this information, now I can start to work backwards and find the current through each one of these resistors, which will in turn help me find the voltage drop across each one and then the power. So if I go up to this one that I just did right here, I now know that the I through this resistor is 2 amps and the I through this resistor is 2 amps. So what that does, that allows me to find one of the currents. I now know that I here is equal to 2 amps. Now that is not going to be true for these two, but I definitely know that here. And using V equals IR, I now know the voltage drop across here as well is going to be equal to 8 volts. But I do know that across this total equivalent resistance, V here is going to be equal to 4 volts. So I worked backwards from here into here, which gave me definite information here, because this was the series circuit right away. I mean, this was its own resistor right away. But now from our rules, we know that in parallel, the voltage is going to be equal everywhere. So even though the equivalent resistance, this is the sum of these two over here, I now know that V2 is going to be 4 volts and V3 is going to be 4 volts as well. Now, guys, we know that our goal is always to use V equals IR, right? So now I have the 2 of the 3 that I need now to find I. So I here is now going to be equal to 4/3 amps, and I3 here is going to be equal to 2/3 amps. So now essentially what I've done is I found the current at each resistor. So I've satisfied this. I found the voltage drop at each resistor. I've solved for this. Now all we do is need to find the power dissipated at each resistor. So at R1, we know that P equals VI in its simplest form. So I can now say 8 volts times 2 amps. At R2, I can use the same exact formula, P equals VI, and that's going to say that 4 volts is going to equal 4/3 amps. And at R3, we use the same exact formula, P equals VI, and we could say that 4 volts is going to be multiplied by 2/3 amps. I do the math and I get 16 watts here. I get 16/3 watts here, and I get 8/3 watts here. And just as a check, guys, when I add up all of these, I'm going to get 24 watts dissipated by each resistor. And a little check, so this is dissipated. A little check is that energy is conserved. So whatever is dissipated must be given to the circuit as well. And where do we give power to the circuit? Well, we do so at the battery. So just as a check, I'm going to say at the battery, VI, that must be the power given to the circuit. So the V of the battery is 12 volts. The current at the battery, which we found out before, was 2 amps. We indeed have 24 watts of power that are given to the circuit. That's really important, and it's a good little check. When you sum up all of the power dissipated or given off, energy is conserved, so it must also be given by the battery. All right, guys, so this is a pretty basic how you work through a combined circuit. You simplify it, and then you work backwards, and you'll be able to solve for everything that you need.